Hello everyone, welcome to our discussion of section 5.1 where we will be talking about integrals. Now integrals are a method in mathematics by which we calculate the area under a curve, under a continuous curve, just like the ones that you see on the screen. Now we've already kind of touched on what integrals are in section 4.7 when we talked about the antiderivatives. The techniques that you saw we used are some of the techniques we're going to be using to find the integral values. With the exception of course, for a curve like this, we have to designate from where to where we're looking for the area under the curve. So for example, for this curve, are we looking for the area from x equals to 0 to, let's say, equal to 5? Or are we looking for the area under the curve from x equals 0 to maybe x equals 3? We will talk about, in the rest of this chapter, chapter 5, which we will look at for the remainder of the semester, we will look at some of the techniques we can use to find the integrals. In Calculus 2, we will continue this discussion in much more detail. But for now, we will just introduce the concept. Now, in this integrals, the main concept that we're going to be talking about in section 5.1 is just going to be the conceptual idea behind the integrals. We won't talk about much details of the techniques of integration or even its notation. We will talk more about that, the integral notation and several techniques in the upcoming sections in chapter 5. But for now, we will just talk about conceptually what integrals are. So for example, suppose we want to calculate the area under this curve. Now it's basically the same curve, but I've drawn two sets of figures. The reason is we're going to use rectangles equally distant or rectangles with equal width under each curve to calculate the area under the curve. We know the area of a rectangle is basically the width times the length, or in this case, the width times the height of the rectangle. So we can calculate that easily. So if we break up the area under this curve into equal segments that are comprised of rectangles of different height but the same width, then we can simply add up the area of those rectangles to get an estimate of the area under the curve. We're going to be doing this in two different ways. But before I mention why I have these two figures, let me complete this figure. And I wanted you guys to see how these two figures differ from each other once I finish drawing them. So in this figure, I'm going to use the right corner of each rectangle to form my rectangle. So in other words, notice that for this rectangle, the right corner is on the curve, right? I'm going to keep that pattern. I'm going to make sure that the right corner of each rectangle is on the curve. For this figure, I'm going to make sure that the left side of each rectangle or left corner point of each rectangle's height is on the curve. And those two ways of approaching the calculation of the area under the curve will produce different errors into our calculations, and then we will use that to talk about the Riemann sum, which aims to reduce that error. But notice that here, for each of these, I have not yet drawn the rectangles, but as soon as I put in the rest of this each rectangle, you know what I mean. Notice the right corner of this rectangle is on the curve, and I'm going to do that for all the other ones, for this one as well. But I have to make sure that these stop at the precise corner point here, like that. Notice that these, even though maybe I can't make them to have equal width exactly manually, but they are meant, each of these rectangles are meant to have equal width. Even if I can't actually produce that on paper as I'm trying. So like that. And then also that. Notice again that the right corner of each rectangle is on the curve. Like that. And that's the last rectangle. So if you use the area of each rectangle to estimate the area on the curve, what do you think? Do you think we're going to have an underestimate of the area under the curve, or are we going to have an overestimate? If you said overestimate, you're absolutely right, because of course we're going to include these regions that are overestimates. So these regions that are outside, above the curve, which we don't want, right? So these regions, and I need to change my pen here. These regions that produce overestimation. Of the area. Okay, these yellow sections, because they are above the curve, but yet in this way of breaking up the rectangles under the curve, we will produce an overestimation. So this is the, let's call this the right endpoints. Right endpoints approach. And we know that this it produces an overestimate, as I mentioned there. Or an overestimate, and let me, in the parentheses, I say overestimate or the upper sum. Upper sum of the area under the curve. Right? And I should add, this will produce an overestimate of this for increasing curves. Notice that this curve is increasing. So this way of using the right point or right endpoints approach will produce an overestimate. If we had a decreasing curve, then this method would produce an underestimation. So it also, the kind of error that this approach generates depends on whether we have an increasing curve or a decreasing curve. So let me add very quickly to this that this would produce the overestimate of the area on the curve when we have four increasing curves. Okay. And I want to add it would produce an underestimate of the area if we had a decreasing curve. Okay, so that's that. So now let's switch over to, instead of using right endpoints, we're going to use left endpoints for each rectangle. So as you can see again, I've divided this x-axis to equal increments, and I might as well, so let's call, even in this graph, I want to make sure that I labeled each width. These are equally wide. Let me call this delta x. So all of these are delta x, and they're all equal. And I don't want to make this drawing too crowded. That's why I put this delta x on every other rectangle. I could have put it here as well. Okay, but that's equally distant from each other, or equally wide. And then this height, of course, is different, right? So each one would have its own height. Now let's do the same thing here on this side. This time, though, I'm going to use the left side of each rectangle to be placed on the curve. So I will do that, and like that. And you can see clearly when we have an increasing curve, this method will produce, using the left corner or left end points of each rectangle, would produce an underestimate. And I guess I have to draw this curve a little bit more, like that. And so this would be that. I think this would be, no, I think that would be sufficient for this one. So this time, because we're using the left side, so we will have this rectangle. This corner, you can already see it's not going to count. Even though it's under the curve, it's not going to count because we're using the left corner points to create our rectangles. So that, and then the left corner of this rectangle. I might have to draw another one here. That would be, I will do it in a second. And then this, and then of course this left corner, right? You're noticing that the left corner of each rectangular bar is on the curve, as opposed to that one, where the right corner was on the right corner of each rectangle was on the curve. And then let me draw another one here. I will maybe here. So we have that. Okay, and then I have to draw the rest of it like that. Okay. Now, of course, you can see that we are not counting this portion, this portion, this portion, that, and this portion that is above this and underneath the curve, right? So all of that, like that. So therefore, these regions that, I'm going to reproduce this, so regions that produce an underestimate or underestimation of the area under the curve we're talking about, right? So you can see that each one of these methods, each approach produces an error, and this would be the left hand or left endpoints approach, and we say that, so this way, this is produces an underestimate or lower sum in this case, so lower sum of the area under the curve, right? And it's obvious from the pictures, from the figures. And of course, let me, just like this one, let me say, and this would happen when we have increasing curves again. For under the curve, and I'm going to do the same thing for increasing curves. And it would produce an overestimate if this was a decreasing curve, just like this one. So if the curve changed to decreasing, like going like that, then this method would produce an overestimate. So let's add that here. The area if we had a decreasing curve. Okay, so like that. All right, so now let's apply this to if we had, as you can see, here we have just how many? We have 1, 2, 3, 4, 5, 1, 2, 3, 4. So what if we narrowed the width of each of these rectangles such that we could fit infinitely many rectangles under the curve. Now that would increase the accuracy, right? If the width of each of these rectangles was infinitely small, then we would have infinitely many rectangles under this curve, and therefore these wasted spaces would be adequately captured in each rectangle, here as well as here. Okay, so let me draw another picture for that. And that's where the Riemann sum comes from. So we want to, like that. So let's draw another picture here. Something like this. Like this, and then f of x. Now suppose we have a curve that is decreasing, increasing, a mix of both, right? Something like this. Something like that. Decreasing and then decreasing here, a little bit increasing and then decreasing again, right? And if we apply the same method of constructing the rectangles under this curve, I'm just going to keep the width wide enough so we can see it, but then I'm going to use this notation to indicate that the widths are getting smaller and smaller, or infinitely small. So I want to then divide this if I can. I don't know if I can divide it into roughly the same width of rectangles. So I'll just try. Like that. The last one, I think it's going to look very different than the rest of this. But it's okay. It's going to help us make the point. Just we need this figure. So I'm going to draw. When we decrease the width of these rectangles, they better fit, or they fit better under the curve. Those wasted spaces that we had, they're going to be minimized. These yellow spaces, which were wasted spaces, here they helped us overestimate the area. Here they are going to help us underestimate. So it's going to be, these areas, yellow areas, are going to be very infinitely small if we decrease the width of these rectangles, as I'm trying to show in this picture. Manually, we can only show this so much. Like that. And then, so these are roughly rectangle, right? But they're not at the top, they're not. But assume that these widths are very infinitely small. Then they would fit under, so instead of this one rectangle, assume thousands of smaller rectangles underneath this. Then they would fit smoothly, much more smoothly under the curve. And this time I'm going to, let's call this A. This is the beginning side. And this B. And then anything in between, well, let's give them a name. So let's say X1, X2, X3, X4, X5, X6, X7, and X8. And X, let's say N minus 1. And I say N minus 1 because N, then we don't know how many N, but N is going to be large. N is going to be the number of rectangles under under this curve. So let's say N. Let me actually define that. So N number of rectangles under the curve, right? So what would that width be? If we just, let's just say that is delta x. We assume that they are equally wide, and let's call this delta x. What would that delta x be? What would that measure be? It would be, so delta x, and I'm going to put it here because it's very important, that width. Delta x would be this length, which would be b minus a, that length, divided by however many rectangles we decide we're going to have. That would be the width of each rectangle. Okay, very important. So that's delta x. And the assumption here, of course, in the previous two figures that I drew and also here, is that the curve or the function that produces this curve is continuous, right? There are no gaps, there are no jumps or cusps anywhere here. It's a continuous curve. Okay, let's actually say that. So I'm going to just assuming, and I'm going to write that here, assuming that the function f is continuous. Function f is continuous. This is a very important assumption for this method to work. Okay. So, and this is a continuous over, of course, interval, the interval under discussion from A to B, over interval A to B. Okay. All right. So then, given that, and delta x, let's also define that width of each rectangle. Okay. So given that, given this width, then the area under the curve, we can calculate it as such. So delta x, so the area under the curve is as follows. We have the function value at each point, let's say, then we can decide whether we want to use the right point or the left point, whether we take the function value at this point or this point or that point. So this would be, let me just draw a couple of these. This, for example, would be f at x6, right? F at x6. This one here, for example, would be function at b. Okay, like that. All right, so the area under the curve then would be the summation of all these areas. Again, I can't draw it manually, but assume that each rectangle under the curve has a width that is infinitely small. And we have infinitely many of these vertical rectangles that you see under the curve. Okay, then the method will produce a very close area estimation that would be as close as a number as we can have to the actual number under the curve. Okay, so then we have f of x1, let's say that value, that the function at that point, times the delta x, right? And then plus the function value at x2 times delta x, and so on. And then plus the function at n times delta x. Okay? All right. So, and this whole thing, then we can call, we've learned about the limits so far. So area would be the limit of that n, right? That function value, limit of all of this, let me actually include it here. Limit of that as n approaches infinity, as we said. So let me move this up a little bit. As n approaches infinity, Okay. So this quantity, which relates to this figure, this quantity is called then the Riemann sum. So A is equal to Riemann sum. And let's use the notation to capture all of this. So it would be the limit of the sum, this sum, 1 to n, and take it arbitrarily large, very large number of rectangles of this calculation, delta x. Okay, and we assume that these widths are equal, so I'm not going to put an index here. The same width for all of these function values. And so then, so as this I, or as n, let's just, as n, the upper sum goes to infinity. Okay, so that's basically what Riemann sum is. It takes the number of these rectangles to infinity. Okay. All right, so of course, the larger, needless to say that the larger this width is, the less precise the estimation. So for the sake of your notes, we can also add that, the note, the larger the width, of the rectangles, the less precise or less exact the estimate of the Riemann sum. Oops, let me move this up a little bit. Okay. So we'll do a few examples just to demonstrate. Like I said, the techniques to integrate are numerous, and we will do a little bit of that in the remainder of this semester, but in Calculus 2 is when we get much more details about that. But this particular section is about how the concept of integration of a function works. Okay, and this is the concept behind that. So let us do a few examples. So I'll start by one example here. Suppose so we want to estimate the area under the graph of f of x. Let's say this is the function for which we want to calculate the area under the curve. Right? You're familiar with this function. And from these are the limits over which we want to calculate the area, from x equal to 0 to x equals pi over 2. Okay. Let's first use the right endpoint approach, right? We're going to do this right endpoint approach, this method, such as the right endpoint of each rectangle is on the curve. Okay, we're going to use this method. And under the graph, with one exception, of course, I'll get to it in a second, and you'll see what I mean. So using just a small number, because for a large number of rectangles, this method will be very, very time consuming and laborious. And the idea behind this whole discussion today in this video is just to get an idea about the concept of integration. Okay, so using four approximating rectangles and right endpoints. Okay, and then of course we also want to ask, is your estimate an underestimate or an overestimate? Okay, like that. So if we draw, and then we'll do one that is using the left endpoints. Okay, well, that would be part B of the same question. Let's for now just draw a basic graph of the cosine function from, not the whole thing, but from 0 to pi over 2. Okay? We don't want to go 0 to 2 pi, just 0 to pi over 2. And then, of course, the y-axis. So you remember the cosine function, right? It starts here and like that. So that's pi over 2. I'm going to stop there because there's no need to draw the rest of this. So this is pi over 2, at which the cosine function is, of course, 0. And this cosine of 0 is 1. So we have this height would be at 1. This would be at pi over 2. And we want to, they say, use four approximating rectangles, right? So we're going to stick with that. So what I'm going to do is try to, let's see if I can break this up into 4 rectangles. So, and we want the right side here to be on the curve. Okay, because of that. So let me do that. Well, let's see how many. Can I break this up into 1, 2, 3, and 4? Right. So let's put the first rectangle here has the left side on that, and then this would be that. So 1, 2, and barely like that. So the right point of the last rectangle, notice, is on the curve on the x-axis. So we're not going to get any rectangle for that. Okay, or we will get, yeah, I mean, it would have 0 area basically, but there is, because it sits, and the right point sits on pi over 2. Okay, with this approach. So let me now draw the rectangles. So we have one here. Let me draw that here. Hopefully the ink doesn't smear on the paper, or at least not that bad. And like that. Okay. So then, so we're doing this. The right side is on the curve, right? Like that. Like that. And like that. And of course, that last one, it's going to be, it's going to have 0 area, but it's there. So we're not going to capture this piece. You already are seeing that this method is going to, and let me highlight it like last time, this method is going to produce an underestimate, right? because we're supposed to get these areas that I'm highlighting, but we're not, right? These regions let me say missed regions, right? We're missing those. Missed regions produce an underestimation of the area under the curve. Okay. What did we say when we talked about increasing and decreasing? We said that if you have, if you have an increasing curve like that, the right endpoint approach overestimates the area under the curve. If you have an increasing function, but what did we say? We said it would produce the same method, the right endpoint approach would produce an underestimate of the area if we had a decreasing curve. What do we have in this case? Of course, we have a decreasing curve. And as you can see, this method, the right endpoint approach, is producing an underestimation of the area. Excuse me. Okay, so we've already defined this width to be equal, and we call it delta x, right? Delta x. And we know that these, so for example, the value of the function at that point, and I want to use my, well, maybe I should use, I'll just do this for a few. I don't want to make this drawing too crowded. Maybe this here and not for the rest. So here, the area, there is a rectangle, but it has a height of 0, right? Because it sits right on pi over 2. So this one, the value of the function here is function at pi over 2, which we know it would be 0. The value of function as here, by the way, let's figure out what that delta x is. We haven't yet figured this out, and at this point I need to do that. So by the way, f at the function value at pi over 2 is 0, and then so what is that quantity, right? We need to know what is that right point, because we want to calculate the function values at right points of each rectangle. So to do that, it's easy. We take the width, which is from 0 to pi over 2, take this, pi over 2 minus 0 divided by how many rectangles we have? 4, right? So pi over 2, so in other words, delta x is pi over 2 minus 0 divided by 4, right? Which means delta x is pi over 8. So that way, then, we know that this is 0. And this here is pi over 8. I don't know how small I can write this, but this one here is pi over 8. Then from here to here is another pi over 8. So from the beginning, we have pi over 8 plus pi over 8, or pi over 4, right? Because it would be 2 pi over 8, which is pi over 4. That's that point. And this here would be, I want to use a scratch paper. Maybe I can use some scratch paper here. But that would be pi over 4. This point will be pi over 4 plus another pi over 8. And in my notes, I have that. What did I get? I got 3 pi over 8. That's a pi. That's 3 pi over 8 is that, which is pi over 4 plus another pi over 8, which is the delta x. Okay? So that the function value at this point is f at 3 pi over 8. Like that. of course, we have to plug it in to figure, and we will do that. And please follow these numbers that I have that are coming up with your own calculator, just to verify them. All right, so using this, the Riemann sum with only 4 rectangles, right, just to see how the system works, this is what we will have. We have the, so Riemann, let's use the Riemann sum for 4 rectangles, and these are for the right points, right-hand points, would be the sum of I going from 1 to 4 for the function at each right corner point. These xi's are on the right corner points of each rectangle, times delta x, of course, right? Delta x. Okay, we already know delta x is pi over 8, right? So then let's calculate this. We have, and we know our function. Let me write it again. So it's on the screen. It's off the screen now. The function is f of x equals cosine of x, a very simple, straightforward function. So the Riemann sum for each of these rectangles would be that summation of that function times delta x. Because delta x is just pi over 8, let's factor it out. So we have pi over 8, that's delta x, times the function at each of these right corner points. Right? That top right corner point has x value pi over 8. That top right corner point has x value pi over 4, and so on and so forth. So let's plug it in. We have f at pi over 8, and then plus function at pi over 4. Let me bring this down a little bit. At pi over 4 plus f pi of pi over 4, and then the function value at 3 pi over 8. Right? And remember that the pi over 8 is out here. The delta x is out here. Plus, of course, f at pi over 2, which is that corner, which will be 0, right? Cosine of pi over 2 is 0. So let's calculate this. We have pi over 8 times the, and these are the numbers I have. Please verify those with the ones you have, you come up with. And let me know if there are any errors. So 0.92. I made sure that there are no errors, but I may have missed 1 or 2. So 0.92. So cosine of pi over 8, you should get that. And then I kept only 4 decimal places. And then cosine of pi over 4, which is square root of 2 over 2. So here's the decimal value that I got for that. And then for function cosine of 3 pi over 8, I got 0.3827. And of course, for cosine of pi over 2, I got 0. Okay, so then multiply each of, or add all of these and multiply it by pi over 8, and this is what I got. Equals, what did I get? I got 0.7908. And please, as you calculate these values, make sure that your calculator is set to the radian mode, okay? If it's set to degree mode, you're not going to get the same values. Just make sure of that. So this, I haven't calculated the left endpoint approach for this problem yet, but you already know this is, when we calculate that, that's going to be an overestimate and this is going to be an underestimate. We already know this is an underestimate, right? So let's just mention that. So this is an underestimate. So underestimated area value, let's say it that way. Okay. And then, so part B, And I don't want to put part B here, but let me go to the next. So I'll just say for part B. Okay, so we have, and I'll bring that picture back. Well, maybe I'll draw another one. I should draw another one because that was right endpoint. So we have like that. So part B, we want to, let me see, what do I want to say here? Use the, let's say, left endpoint approach or left endpoints for this calculation. And then let's answer the same type of question. Is your estimate an underestimate or overestimate? Okay, so I'm quickly going to draw another picture here. We need that because we're going to use a different approach. So here, maybe drawing here. And then again, once again, I start, this is the cosine function from 0 to pi over 2. And let me once again break this up into some equal increments along the x-axis. Maybe a little bit larger than a half a centimeter. This is the centimeter side of my ruler, so 2 and 3. I don't think I did such a good job of dividing this, but this is as best as I can do manually. And then so this time we are using the left endpoints, so I got to be careful how I draw this. So we have, okay, so this side along the y-axis would be one of the sides, and I want to, hopefully I don't want to smear this ink. Let's see, so we have, so there is like that. Right? You can see already that it went over the curve, which means we're going to have an overestimation if we use the left endpoints, right? Because the left endpoints now are going to be on the curve right there. Okay? And then also, so then the next one will be here, right? Right there, the left endpoint right there. We take that, and then over like that. And then I know these rectangles should be have equal width, but it definitely doesn't. And then here for us, so another one here, all the way to over pi over 2. Okay. So please assume that these widths are all delta x and equal to each other. Okay, and so that's using the left endpoints, and of course we're going to have an overestimation. So regions that will produce an overestimation. We already know whatever number we get, it's going to be overestimated of the area. And just like last time, delta x is simply pi over 2 minus 0 divided by 4, which we were told from the get-go to use 4 rectangles. Okay, now this time, the 4 rectangles have a substantial height in the previous one, because one of the points was right on, the right point was right on pi over 2, we had 0 area for that one. Okay, but this one we have the area for all 4. So, okay, so let's add up the same formula for Riemann sum. We have, this time we have the left endpoints, right? Left endpoints for 4 rectangle would be equal to all of those. So we have from 1 to 4, and then the function, so this would be the function value at each point. So this would be, let's see, we have the left point, so that would be that, this, that, and that, these 4 points, right? And hopefully the drawing is not going to get too crowded, but that's pi over 4, like before, pi over 4, that point, and sorry, pi over 8 I meant, pi over 8. That's pi over 8 here, because each increment, as we said here, each delta x goes from 0 to pi over 8, and then pi over 4. So that one is going to be pi over 4, and that one, it's going to be 3 pi over 8. Let me put an arrow there, 3 pi over 8. So the function value at each of those I values times the delta x. Of course, we're not going to calculate the function as pi over 2, right? Pi over 2 would be the right side. This time we're taking the left endpoints. Okay, so we're taking these values. The last one would be 3 pi over 8. Okay, so calculating, we have, I should mention that, like that. So this would be cosine of, let's see, cosine of 0, right? Because the left point for this rectangle, the left corner point would be cosine of 0, right? Cosine of 0. So we begin with that. And of course, delta x is pi over 8 for all of these. So I'm just going to put pi over 8 as a factor out here, and then say cosine of 0 plus the next one. I'll try to keep this on the screen if I can, like that. And so cosine of the next left point for this rectangle is cosine of pi over 8 plus cosine of pi over 4, which is the left corner point for this rectangle, plus cosine of 3 pi over 8, right? Which is the left point for this rectangle. Cosine of 3 pi over 8. Okay, so now these are the numbers I have. please compare them with your own calculations. And this would be 1. Cosine of 0 would be 1. Cosine of pi over 8 would be 0.9239. Cosine of pi over 4 would be 0.7071 plus 0.3827. And we have, so pi over 8, add all of these, multiply by pi over 8. And of course, just like before, please make sure that your calculator mode is set to radians. Okay, if you have degrees, you're going to get the wrong numbers here, even if you punch in the right numbers. And so I got 1.1835. And this is, as we mentioned, this is an overestimation. So overestimated area value. Okay. Let's do another example with a different curve. So this was decreasing, right? This curve was decreasing. Let's do an example with an increasing curve. And we want to, so we want to do the same thing. Let me bring back my, so here is what we want to do. We want to estimate the area under the graph. At this time, of course, our function is different. So we have f of x equals square root of x. And let's see. We want to do the same thing. Divide the curve on area under the curve to 4 rectangles. And we want to go from 0 to 4. 0 to 4. Let's do it from 0 to 4. From x equals 0. Let's make it easy. So x equals 0 to x equals 4. Simple, straightforward division of 4 rectangles, right? Okay, so, and then we want to do that. Part A, of course, we want to do the same thing. We're going to using 4 and right endpoints. And we want to ask the same thing. Is your estimate an underestimate? Or an overestimate? Okay, like that. All right, so here's a graph of the, I'm sure you're all familiar with the graph of the square root function there. It has an easy, straightforward graph. So let me draw that here in this corner. I'm going to exaggerate this curve a little bit because to make it easier to draw the curve rectangles underneath it. It's a lot more flatter. It's flatter than what I'm going to draw it, but it's just going to make it easier to show the rectangles like that. And we're going to go to, let's go just from 0 to 4. And 2, 3, and 4. So let's see, 1, 2, 3. So 1, I guess 2, and 3, and 4. I barely fit it here. So 0, 1, 2, 3, and 4. And using the right point approach, we're going to make sure that the right side is on the curve. So let's draw them. I'm going to draw here. That way I don't have to worry about smearing the ink all over my paper. So I'm making sure that the right endpoints are on the graph or on the curve. So that and that. All right. That's that one. And then another one here. Making sure that the right endpoint is on the curve. Drawing it from here to here. Like that. And then again, making sure that this right endpoint of the rectangle is on the curve, like that. So what do you think we're going to get? Do you think we're going to get an underestimation or an overestimation? It's clear, right? Look at all this extra space, extra area. We're going to get an overestimation. It's clear. Like that. So these regions will cause an overestimation. Okay, so this is regions cause overestimation. Like that. And of course these other ones too. All right, so we already know that. Then we also know that the width here should be delta x. Let's calculate delta x very quickly. Delta x is 4 minus 0 divided by how many rectangles? 4. Right? So delta x is equal to 1. Right? Very straightforward there. So then the Riemann sum would be the value of the function at the corner points, at these points, times delta x. right? And of course that one. So f of x at that point, so f at 1, f at 2, function at 3, and function at 4. So f at 1, f at 2, f at 3, and then the right, we're using the right end points. So this would be f at 4. And of course, each one times the delta x. So the Riemann sum would be, let me move this up like that. And this would be the right endpoint. So R4, it would be the I going from 1 to 4 of the square root of, I'm just going to write the function, square root of xi, right, times delta x, which is 1. So we'll have, move this up a little more. So we have square root of 1, it's just going to be out here, right? That's delta x. And let me put it out here in front as a factor. And then each calculation would be square root of 1 plus square root of 2 plus square root of 3 plus square root of 4, of course. Like that. Okay. And so if we add all of this, so this is what I got. Please don't trust this value. Calculate this. I got, when I calculated all of this and, of course, rounded some of them times 1, this is what I got, 6.1463. And we mentioned that here the function is increasing, not decreasing, and it's increasing. And this method of using the right endpoints will produce an overestimation of the area under the curve. And so this value is an overestimate. So part B, we're going to do the same thing using the left. I'm going to keep this. Maybe, we can keep this, but this time we will be using, well, no, let me actually draw another one for this. I'll just draw approximately. So again, repeat part A with left endpoints. Okay, so let's do that. I'll just draw a graph here. Like this. So I'll just do this to make sure that the rectangles are easier to see. Four, so let me, I guess I can 1, 2, 3, and 4. Maybe I won't need that last one, but so this time from 0, 1, 2, 3, and 4. So this time we're using the left endpoints. So this one, clearly that's just at 0. It's not going to give us any rectangle. And so that would be then, the next one would be here. So that one would be right here, which is 0. All right. So that's the left point of that. And then the left point of this rectangle would be this. And that. And then, of course, the last one would have the left side here. And then here. Maybe here, like that. Okay, so let me just draw that. The left points, right? That's the left point of that rectangle right there. The left of that one is on the x-axis, which produces 0. Okay, so we're losing considerable space under the curve there, right? And then here, so what do you think this calculation will produce? An overestimation or an underestimation? You can clearly see that it's going to produce an underestimation of the area under the curve, right? Because we're losing all of this. We're losing that space, this one here, and that one. So these regions produce an underestimation of the area. Okay, like that. All right, so the left corner points in this case are that one, the function value on the curve, that point is on the curve at 0. Then the corner point here would be, let's see, so that's the left corner point of this rectangle. So that would be f at 1. This would be f at 2. And then finally, that one would be f at 3. We're not going to have the function value at 4, right? Because that's right corner point. We're using the left end or corner points here. Okay, so that's all. And then for the left side, the Riemann sum will produce, and delta x, of course, is the same, right? So delta x here is equal to 1. We have 1 times each of those function values, f at 0 plus f at 1 plus f at 2 plus f at 3. And then, of course, the sum is, so 1 time square root of 0 plus square root of 1 plus square root of 2 plus square root of 3. And according to what I have, I ended up with, let's see, an underestimate. I think I need to recalculate this because this number that I have, I can't read that. My notes are pretty cluttered. So this would be just 1, and then this is 0, 1. So we have, 0 plus 1, this would be 1.14.14, and square root of 3. Square root of 3 would be, let's see, I get 1.732. So add all of these plus 1.414 plus 1. Okay, so 2.414 plus 1.732. So yes, so that number that I have is, okay, now makes sense. So it's 4.1463. Okay, and clearly this is an underestimation or an underestimate of the area under the curve. Okay, so it's like that. I hope it's starting to make sense how integrals work, because after this section, in the coming sections, we're not going to do this again. We're just going to use the usual techniques of integration, and which will be much quicker and much more efficient, and then but it will produce a very exact result. So then let's do one more example. This would be page 6. So this is a basic word problem. Find lower and upper estimates. So we're going to do the same. Use the right corner points and the left corner points of the time intervals to do our estimation. Find lower and upper estimates. Distance. Okay, so this time we're estimating the distance that she ran. Okay, here is a table of data values, and so we have, should draw it here, maybe somewhere here. And then of course here, and then so here. And so here we have, this is time in seconds, but let me move this up. So this is cumulative time in second. In seconds. And then speed or velocity, and this is measured in feet per second. And then we need 1, 2, 3, 4, 5, 6. So let me 1, 2, 3, 4. Let me see, 1, 2, 3, 4, 5. So 2, 3, 4, 5, 6. So we have one. I need 2 more here. These are a little bit smaller, but these are the times. So we have 0 and then 0.5, 1.0, 1.5, 2, 2.5, and of course 3 seconds. And then so 6.2, 10.8, and 14.9. This is cumulative speed, of course. So cumulative time and cumulative speed, as her speed is increasing here, and 19.4 and 20.2 feet per second. Okay. So for the low sum, or lower sum, right? We're using, if we take each of these as intervals, then for the lower sum, from here 0 to the end of this interval. So these intervals, we got to be careful because they overlap. So from here 0 to 0.5, we assume that we had a stopwatch, and at 0, so then we record the time and the speed. Of course, at time 0, speed 0. So the runner is at standstill. Then the runner starts, and either us, or either a human being or a machine, is clicking the time and recording the speed at 0.5 second intervals, right? Very quick intervals. And these are what we're getting, the speed at each stopwatch interval. So, but these are going to, the beginning and the end of each interval is going to overlap. So we're going to have, these are the intervals we're talking about. So from here to here is one interval. And then, I mean, don't let these bars that I've drawn distract you, because these bars are just to keep the data in line and organized. But the red, this represents one full interval of a half a second. And then and then another one would be from here to here. I'm hoping you can see how this is working. So the second interval is from 0.5 to 1 second. Then this interval would be from 1 to 1.5. Do you see how they're overlapping? And then from 1.5 to 2. And then 2 to 2.5. And then finally 2.5 to 3 seconds. Like that. So let me, like that. Okay, so if we're using the lower sum, then let's see. So we're using this. We have, each interval is 0.5 second. So that would be 0.5 times 6.2. So that interval, so this just, it's going to drop out, but 0.5 times 6.2, 0.5, 6.2, and then let's see, so that would be 10.1, 10.8 times 5, and so that would be that. So 10.8.5, and then 14.9 times, so that would be like that, 19.4. So 19 point, for the lower sum, 19.4 would be the last one to calculate, right? So I actually should have drawn one here. So 0 times 0, it doesn't, this one, it just drops out. So this one would be 6.2. So this would be 6.2. And then 0.5 plus 10.8 times, so 0.5, the interval times 10.8 plus, so, and then because this one doesn't count, and then 6.2 for that interval, 6.2, and then for this interval, that would be 10.8 times. So this is for that interval. This piece is for that interval from 0.5 to 1, and then 14.9 for this interval from here to here. That would be 14.9 to. But this way of calculating, you'll see it'll generate the lower sum, as opposed to, because this is where we're going to stop. We're not going to include 20.2, and the upper sum will include the 20.2. So, and then 18.1 times 0.5 plus 0.5 times 19.4. Okay, that's the lower sum. So we stop there. If you add all of this, hopefully your answer will agree with mine. 34.7 feet is what we estimate the runner must have run, and the upper sum would be 0.5 times 6.2 again, right? That's for this interval. For that, 0.5 times 6.2. So for the beginning interval, for the lower sum and the upper sum, this interval is 0.5 times 6.2, but it's the upper, the last interval is where the lower sum omits that piece, 20.2, but we will include it here. And then instead of 19.4, we'll include 20.2 plus 0.5 times 10.8. So that last interval is the only difference between these two. And then plus 0.5 times 14.9 plus, move this up a little bit, and then plus 0.5 again times 18.1 plus 0.5, 4, 5, 6, so 1, 2, 3, 4, 5, so 6, and then point, and then 0.5 times 19.4, so that's for that interval, and then this is for that interval, 0.5 times 20.2. So that upper sum we get 44.8 feet. Okay. All right, so this was basically basically a very superficial look on at the Riemann sum and how integrals will work, and I look forward ahead where we actually use integration techniques in the remaining sections of this chapter. And I want to thank you for watching this video until this point, and for now have a nice day, and I'll see you again next time.